language games. So just a disclaimer, I don't actually do math. I'm a computer scientist. I write a lot of code. So I'm going to show a bit of what I'm working on and one mathematical result near the end. Okay, so oops. Okay, let's just try the keyboard. Okay, so my motivation is I want a flexible communication system with computers. And computers have a very rigid action space. And the question I'm posing is, can we do better than just programming and having people learn exactly what the computer action space is? And to do this, I want to model the process of agents here, the human and the computer adapting to each other. So I just want to give a few examples of adaptation and why you want to be adaptive. So here is a sentence you might say to the hotel front desk. Hello, please wake me up at 9 a.m. tomorrow for my flight. Thank you very much. So there's lots of features in the sentence expressing your intent. Such as you're catching a flight, so that's pretty important. And if I'm not waking up, you should insist. There are things like expressing manners, which makes other people more likely to do what you want to do. And there's a little bit of redundancy, right? Just in case that others can't understand. Okay, but on the other hand, if you just have a computer action space, like your virtual assistant, all it does is something like setting an alarm, right? And the action space is just take some time and it sets an alarm at that time. Then all these features of the natural language doesn't really matter if that's the computer action space. And as a result, it might make more sense to just say something like set alarm at 9, and you can even ignore some syntax and just say alarm at 9, which kids actually find very natural when they interact with the virtual assistants today. Okay. So to model this process, I propose to study this thing called language games. In some sense, it can be traced back to Wittgenstein, who said that language derives its meaning from use. So a particular instantiation of this is what we call a learning language game. It's an iterative cooperative game between a human player and a computer player. So the human player has some goal to accomplish, but cannot perform any of the actions directly. So it uses language and provide feedback to the computer. And on the other hand, there's the computer player, which does not know the goal, but can perform the actions. And in the beginning, it does not understand the language. So to be successful at this game, the human must teach the computer a suitable language and adapt to the computer action space. And on the other hand, the computer has to learn this language through interaction. And more, well, I'll show one example of this, which we call the should learn. So this is an instantiation of that game in a blocks world, where the goal is to get from some starting set of blocks to an end set of blocks. So the human would produce some utterance, such as remove red. The computer initially just returns a random list of actions, sorted by how likely the computer thinks the utterance corresponds to that action. And the human pick one of those actions and then the computer performs a learning update. Okay, so together they arrive at a language and they make a little bit of progress. But there's really no restriction on what the human can say, and the computer just implements a particular learning algorithm and do its best to fit to the human data. Let's see. Okay, so so we can test this. Hopefully it works. Oh, maybe I'll just get rid of the pointer. Oh, sorry. Wait. All right. So there is a final state. I would say something like remove cyan. Do I have internet? Oh. Okay. Oh, not sure if I have Is there internet in this room? Or, there is. Okay, maybe let's just skip this. I think you can. Well, hopefully I explained the setting well enough without actually trying this. So yeah, so the task is map some natural language sentence to this computer action space, which has a particular structure. I'll show instead then what some of the players did. So as you can see, people employed all kinds of strategies, and we can briefly say categorize, classify them into things that looks like English, things that look like computer code. So in particular, let's say look at this add x red block. You can almost immediately understand what this would mean, right? But it's non-trivial to translate this into a particular computer action space. Okay, so I should have another application which kind of which should work. So this is for manipulating some plots, where you might say things like red bar, or maybe this also doesn't work. I thought this should be local, right? Yeah, okay, so red bar, and we will turn some, the leftmost plot is the initial plot, and the system returns some candidates. You can maybe say something like right, and then there's a bunch of ways to make it hollow. You can be a little bit technical, right? Use the actual language, say field. Then there's a bunch of actions that you can do, right? Like here, removing the x-axis labels, whereas if you say, let's see, right, if you say label, then it likes to remove the A. If you say labels, it removes all the letters.
But the point is,
right? Yeah.
The point is that it learned how to do this like iteratively. It's not like a human program.
Yeah. So right. So this is learned from data. Yeah. Yeah. Don't program any keywords. Okay, but this is the motivation of why I'm studying this kind of problems. Okay, so I would just want to look at one formalization of this that we're looking at as a communication game. In the setting, nature picks a meaning to be communicated, and there are two players, the speaker and the listener. So based on this meaning, the speaker sends a message, and then the listener observes this message and reproduces another meaning, y prime, and they both get a reward if y is equal to y prime. Right, so just the reward of one for if they communicate successfully. A specialization of this is to say, you can't just pick arbitrarily. You have to have a fixed distribution, and all you can do is sample from that distribution for both the speaker and the listener. Okay, and if we do this, then there's a clear notion of expected accuracy. So this is assuming that nature picks all possible meanings at uniform. Okay, which is just the sum over meanings and sum over what you can say for that meaning. Right? It's the expected reward. And furthermore, if we say that the space of meanings and utterances is actually just a discrete space, then the speaker and listener are just matrices, big P and Q, right? So where the sum of each column of P is 1, and the sum of each row of Q is 1. And the expected accuracy is just the inner product, element-wise inner product between P and Q. Okay, so a pretty simple game. What can we say about it? Okay, so one concept we can look at is equilibrium, right? So here, let's consider a language as a pair of this of a speaker and listener matrix, unrestricted. Where the listener doesn't actually have to correspond to the speaker, and the expected accuracy is just the sum of inner products between the speaker of one language, the listener of the other language, and the speaker of the other language, the listener of the first language. Right? Basically, how accurately they can communicate if they are speaking in turn with equal probability. Okay, well, let's just do the Nash equilibrium. So a language is in Nash equilibrium if one party does not benefit from deviating from that language, right? So you can't improve the accuracy if you just unilaterally change your language. Okay, so and here is one result of what this matrix, just on what this matrix has to look like for it to be in Nash equilibrium. Okay, so Yeah, so this is actually work done here some almost 20 years ago. Right, but really pretty, very simple math. So it's Nash if the speaker and listener matrix has the same support, and each row of the speaker matrix has only two values, either 0 or some other value. Okay, so yeah, so all Nash equilibrium has to look like this, where so the speaker matrix have identical values in each row. Listener matrix has identical identical values in each column. And the reason is pretty simple. If because we're just looking at the inner product, well, one of the well, I think this is the main reason. So because for Q, the row sum is 1. So if in the P matrix you have different values, then Q can just put more mass on the larger value to improve the accuracy. Right, and it's also should be pretty clear that if you're corresponding, if your speaker and the corresponding listener doesn't have any non-zero, have a 0 at some spot, then you shouldn't ever put a non-zero mass. Okay, so that's the form of Nash languages. And okay, and here is a simple consequence of Nash languages. Recall in the definition we didn't care about what P and Q are, right? They could just be unrelated speaker and listener. But here we are saying if the language is a Nash language, then the speaker and the listener must have a consistent joint distribution. And the reason is again pretty simple. So if we define the support of a matrix as the 0, 1 matrix, where you have a 1 for every non-zero value, then the speaker, both the speaker and the listener, can be written as a diagonal matrix times that support matrix S. So merely setting the joint distribution as the two diagonal matrix multiplied by the support matrix gives the joint distribution, which is fairly reassuring, right? If you're in equilibrium, then your speaker and listener must be consistent with each other. Okay, so that's a flavor of the kind of problems I'm thinking about. So what I'm doing here are looking at algorithms to find these communication equilibriums. In particular, expanding these results where you have matrices to where you have a learning model, which corresponds to very large matrices with some structure and constraints. Yeah, and looking at if we can have better learning methods than just fitting to a data set, since we are expecting the other player to adapt to the system, so the data set changes. Okay, that's everything. Thank you.